So I will start with the equation again. And at the end of today, I'll mention some other equations for which a similar analysis might apply, some open problems that you can consider once you get acquainted with the known results in this area. But so this is focusing analysis. Plus, and then we were discussing last time the L2 critical case, such as P equals 1 plus 4 over D. And then we motivated the need to pass from the ground state well, I'll just write, so let me write P minus 1, Q equals 0. Ground state to a modified equation. So there's this variational characterization for Q, which tells us that the solution U to this L2 critical NLS that blows up, that has a mass slightly larger than that of Q, has to match Q asymptotically. But we find that through a spectral analysis of Q, of the linearization of NLS in a neighborhood of Q, we find that there are missing directions, and we should extend Q to a function Z. And the function Z solves this more complicated equation. That. Okay, so there's now two extra terms, and the lambda, the capital lambda, is an operator associated to scaling. It's d over 2 plus x or y. I tend to evaluate z at y now because I'll do a substitution in a moment where we change x to y. So let me write like that. So lambda. Lambda is that operator. Okay. So then here you're taking P equals to 1 plus 4 over D. Now there's a separate motivation, which is actually historically how it came about, a separate motivation for considering this equation, which was an ansatz for supercritical blowup proposed by Vladimir Zakharov in 1984. And that is so a separate motivation. So now consider supercritical. Yeah, 4 over D less than P. And you should stop when it becomes energy critical. Definitely by then, the story will change. But actually, what I'm about to show you has only been rigorously established for P close to critical. The slightly supercritical regime. It would be nice, it's still an open problem to construct the blow-up solution I'm about to describe when P is equal to 3 and D is equal to 3. So when D is equal to 3, this is just 1 plus 4 thirds. So we're far away. We're deep into the supercritical regime. The L2 supercritical regime. In fact, the critical exponent in that case, D equals 3, P equals 3, is sigma sub C equals a half. So Zakharov, in this case, had proposed, and this is 84. It can be hard to get a hold of these Russian papers, at least in English translation. He said consider a so-called self-similar ansatz. So this is a typical thing to do when you have a nonlinear equation and you have a scaling. You look for a solution in which the scale changes with time, and then you hope that by just giving the scale parameter time evolution, you can reduce to an equation which is independent of t. So you just assume lambda is some unknown function of t, and then I also will change time from t to s. Just plug this into this equation and get an equation for phi. So this gives the following equation for phi. Lambda plus sigma sub c phi plus. So it's a modified version of NLS. There's now this extra term. So lambda defined here, when we look at lambda plus sigma sub c, we get 2. So we recall that sigma sub c is it's the critical Sobolev exponent, and it's given by the formula d over 2 minus 2 over p minus 1. And I'm sorry, it must mean minus, because it's supposed to give me 2 over p minus 1 plus y dot gradient. And that is what you get when you differentiate this equation with respect to lambda. Should be a minus. Okay, so then you reduce the problem from finding a solution u to finding a solution phi to this equation. Yes, and so the choice of s has been made so that the lambdas factor out, and that choice is given by ds dt. S, depending upon time, should be given by ds dt equals 1 over lambda squared. Because each of these terms have a 1 over lambda squared in front, and so you want to have the same factor in front of the dt to ds. Okay. So then if you take, so now seeking a solution phi to this equation, you take phi of y comma s equal to e to the is z of y, then you get the equation that we have over there. If we take lambda s over s to be minus b, then we get the z equation. We'll call that star, with sigma equal to sigma sub c. So that's this equation. Yeah, so you have the lambda operator minus the sigma. All right, sigma equals sigma sub c. So this you want to be constant. And so then the question is, so what is the relationship between sigma and b? So it's by studying this time-independent equation, you find that there exists solutions there exists a lot of solutions, but only a restricted set of solutions in which Z has finite energy. Because the energy requires a special asymptotics at infinity. So in order to achieve finite energy, you need to take sigma equals b to the minus 1 e to the minus pi over b, approximately. So first, a leading order term. And so for this problem, you have a desired value of sigma. You want sigma equals sigma sub c. And then you have to find the b that makes equality here. So you're given sigma, find b. But if you assume that that's possible, and it's proven to be possible if we're working close to criticality, so sigma sub c is very small, close to 0, then we can construct the z's solving that equation. We have an asymptotic expansion for this relation, which can be inverted, and you can get b in terms of sigma. Right, so you get a solution. So then lambda sub s over lambda is, via this relationship, it's equivalently written as lambda t. And you want that to be a constant. So then integrate, and you get lambda of t squared equals it's the square root of 2b. I think it's, I'm sorry. It's 2b t star minus t. Right? Yes. Okay. Right. So so t star being the blow up time. So then we have a formula for the rate at which we blow up. And then now that you have lambda, you can go back and get s. So ds dt, which is 1 over lambda of t squared, is then given by 1 over 2b t star minus t. And so s of t is equal to 1 over 2b times the log of t star minus t inverse. So as t approaches blow-up time, you have s of t going to plus infinity. So it's this equation solved time s up to s to infinity gives us a solution to the u equation up to blow-up time t star. And we have assigned specific values to all of the a priori unknowns. So the lambda has been specified, and the s has been determined. And then the b isn't related to the sigma sub c via that formula. Sigma sub c is that. So this is called the self-similar solution. And if you compute the gradient of u in L2, then you find it's comparable to t star minus t to the minus 1 minus sigma sub c over 2. And earlier we had proven that any blow-up solution must satisfy that this is bounded below by that. So it's an explicit, if you take z as being known, it's an explicit blow-up solution blowing up at the slowest rate possible. Okay. So that's why people started looking at this equation. Yes?
In respect to the initial data of the Sakharov equation, somehow special could be any initial data?
Well, she's just looking for a solution, so not trying to solve an initial value problem, just looking for a solution. So it's given at any time t by the formulas. If you take phi equal to e to the I s z of y, put that here, then that's the formula that you can evaluate at any time. All right, so quite a bit later then, it was realized that you can use z to give a form for L2 critical blowup. So we can actually take sigma sub c equal to 0. And the modification required is that sigma is no longer sigma sub c. Sigma sub c is equal to 0. But we still have a sigma, and we allow it to vary in time, and it dynamically goes to 0, and b goes to 0 along with it. We still have this, this relationship that sigma is like minus b inverse e to the minus pi over b. That relationship is still intact. But now, so now we're doing this case. Now b of t will go down to 0, and sigma along with it as t goes to t star. Okay. So the way it's figured out is you start with the same substitution. So start the same way. So now 2 over p minus 1, we might as well write as a d over 2. So suppose we're looking for a solution of this form, and we come over here, and now there's sigma sub c is 0, so we really have just lambda phi. But then you still work with this model. And so it's a little convenient to introduce the phase shift. So now let psi be given by e to the minus is phi of ys. And that just has the effect of changing the equation a little bit. So now it's I ds psi minus I lambda s over lambda, capital lambda psi plus Laplacian psi plus psi to the p minus, well, now it's 4 over d. Psi equals 0. Which you can write in a nearly Hamiltonian form. So going back to the notation that we used, the functionals that we introduced last time. This. Okay, so M, V, and H. So H is energy. So we have M of psi, 1/2 L2 squared, and then you get M prime equal to psi. You have V of psi is 1/2 imaginary part, psi bar, y dot gradient psi And then v prime becomes minus I. I'm sorry, it's like that. Right, yeah, that's fine. Okay. That. And then H is just the energy. And so this is just another way of writing that. So this is not quite Hamiltonian because the lambda s over lambda actually does vary in time. But if it's slowly varying, then perhaps the same type of analysis will be valid, and that turns out to be true. So because this will be approximately b, not exactly b, but to leading order equal to b. And then b, the s derivative of b, will turn out to be of much smaller, of order sigma, and sigma is then exponentially small in b. And so as a result, you do have a parameter that's changing in time, but it's changing very slowly. So you can sort of regard this as being a new Hamiltonian equation, where the new Hamiltonian is not h, but it's m of psi plus b, v of psi plus h of psi. So last time, recall that we were working with this A of u, or A of u, which was m of u plus h of u. And then that had the property that A prime at q, the ground state, is equal to 0. So it's just m prime of q plus h prime of q is equal to 0. So you have a stationary point for this functional, which is q. Now, let's work with b of psi. Changed our frame of reference from u to psi, which is yeah. So let's just say it's equal to this. So this will be b of psi. But it turns out that b prime of z is almost equal to 0. This b prime of z will be equal to z minus ib lambda z, coming from v prime at z is this term. And then you have minus Laplacian z minus z to the 4 over dz. And that's not exactly the equation for z, because there's also that sigma term. So this is equal to IB sigma z. And so we have, which is small, so it's not exactly a stationary point for this functional. But still the same principle applies. That we should consider solution psi to this equation that is close to z. So now we do an expansion. Psi is equal to z plus a correction, call it w. Plug it in here. And you get the linearized equation. So you say, well, I will look for psi y comma s, which is z of y. That depends upon b, plus w y s. Then you plug in, and you get now you have to take a s derivative, the left-hand side is ds psi. S derivative of this, the b depends upon s. So we get db z of y with a b sub s, the s derivative of b, plus dsw equals, okay, so that's the left-hand side. And then on the right-hand side, we're taking psi equal to z plus w. And so then you Taylor expand each of these functionals. So the first term is the j is minus I, if you recall, is this one. Right, and then it's the next term would be W. Yeah, the second derivatives here are operators, and this is now the linearization around z, and then the z has the property of being nearly a stationary point to this equation. So this reduces to, so the j is minus I, and then we computed that this becomes, so actually it's minus, it's minus. I'm sorry, it's minus. So then minus I times minus IB sigma z. And so what you're left with is this new linear equation. Of course, then that goes on to the second order in W terms. And if W is small, that will be negligible. So we're left, though, with two inhomogeneities. We're left with this term and this term. And they have to be orthogonal to the kernel of this linear operator in order that we could solve for W. That is, in order that we could carry out the expansion to the next level. Or at the more, for the more rigorous analysis of this problem, that that you could achieve the coercivity for W, the dispersive estimates that you want to prove for W will only be available if W satisfies a certain orthogonality condition with respect to the kernel. And therefore, the inhomogeneity has to respect that. Okay, so we have the way we were describing these problems last time was that there's really 4 parameters, and I've suppressed some of the parameters. So in more detail, you would include a phase, gamma. You have lambda pertaining to scale. You have this b, and then there's the other parameter, beta. You include the 4 parameters. Gamma, b, beta, and lambda. And so you would look for psi ys of the form e to the I gamma z b, but you would also allow modulation in the beta direction, which I've suppressed from the brief description here, y, and then plus the w. So we'd actually be able to move in all of these directions. The lambda has already been taken care of here. And then we view this as a projection problem. We have that the psi is evolving according to a Hamiltonian or nearly Hamiltonian equation, and then we're projecting the dynamics onto the submanifold that is spanned by varying the parameters. So we have psi, and then it is projected onto a manifold M, and M allows for, it's the four-dimensional manifold that's obtained by varying all these parameters. And so then you want it to be an orthogonal, a symplectic orthogonal projection, because that will decouple the Hamiltonian dynamics into directions parallel to M and directions symplectically orthogonal to M. And so you impose orthogonality conditions that are really symplectic orthogonality conditions. And they are W J inverse, because that's the symplectic pairing, derivative with respect to gamma, so the tangent direction when you vary gamma is I times Z, so that should be equal to 0, and then W J inverse, you vary the scale, and you get lambda Z, that you vary the B and the beta, and you get two others that we'll write the one for varying B actually turns out to be this. And then the one for varying beta is a little harder to write, but you could put it as this rho. So it'd be actually e to the minus 1/4 I y squared rho. Although the beta doesn't play much role in the analysis, and so actually, if you look at the Merle and Raphael papers, they changed this orthogonality condition to one that's slightly skew, and it's still, the analysis is still valid. Right, so you need 4 orthogonality conditions in order to describe this decomposition of psi into something that is W, which is symplectically perpendicular to M, and then movement along the manifold M. And so from these conditions, you can then recover the dynamical behavior of these parameters. The dynamics should be that of Hamiltonian motion for the restricted Hamiltonian to M, but at the more technical level, you take these conditions and you take an S derivative of these equations and you plug in the equation and do some manipulations, and out comes the equations for the parameters valid to leading order. Among them will be the one that I've already sort of assumed, and that was lambda S over lambda is like minus B. So that'll come out by taking the s derivative of one of these equations, plugging in the equation and going. The one that I want to focus on, because it's the key to understanding where the log comes from, is you take this orthogonality condition and you take the s derivative and see what you get. Okay, so take ds of this condition. So if j is minus I, j inverses I, so this is the same thing as wz. Okay. So you'll get dsw out of this. And so you then have the ds equals stuff, among that being this inhomogeneous term. So you have dsw is equal to minus bs dbz minus b sigma z plus, and then we have the rest that's over there, right? So the orthogonality conditions will come into play to say that when you plug this in, you should get 0. And so what you need is that this paired with that equals 0. So it's saying that this inhomogeneity is not exciting modes in the kernel, which would lead to instability or movement away from this decomposition. So we need minus bs dbz minus b sigma z, and paired with z equals 0. So that is minus b sub s db of z in L2 squared with a 1/2. That's this paired with that. Minus b sigma z L2 squared. Okay, so then we get b sub s is b sigma z L2 squared over to 2 here, and then this db z L2 squared. So the z depends upon b. So in fact, z, if you take the whole profile z, it has infinite mass. It has to be cut off at a large distance. It's among the many technical details of this problem that complicate it. But you can cut it off at radius sigma to the -1. That's the appropriate truncation point, and then the analysis is still intact. But z, it turns out, has the leading order description in B given by this. So then you get an expansion where the dominant term is this quadratic phase times q. Next order term is of order b squared times rho, and rho is this L plus inverse of y squared q. So that, we haven't seen that yet. I haven't described the calculations that lead to the construction of the profile, but this is what comes out of that. So then if you compute ZB in L2 from this formula, what you get is Q L2 squared plus 1/2 B squared Q paired with rho. And this can be rewritten, turns out, as with some integration by parts, using the fact that L plus of lambda Q, I'm sorry, L plus of lambda Q is equal to minus 2Q, and some integration by parts, you can get that this is 1/2 YQ in L2 squared. All right, so what you have is a constant plus a quarter B squared times YQ squared, another constant. So when you take dB of that, you get 1/2 B Y times this constant Y L2, YQ L2 squared. Okay. So let's take that and put that in over here. So it's just comparable to B, and you have a B up here. And yes, I forgot a minus. Okay, good. So I forgot a minus. And so it's comparable to minus sigma. So it's some constant times minus sigma. And the constant, it turns out, is not important. So I just use this notation for constant times minus sigma. So you get that Bs is proportional to minus sigma, and then sigma is given by this B inverse e to the minus pi over b. Yes, it does. But the beta is comparably smaller and not as significant in the analysis. So I have tried to simplify the presentation by removing the effects of the parameter gamma and beta, and just focusing in on the z, the b, because it's this term combined with that term, part of the inhomogeneity in this equation, that plus this condition, which gives you the key equation for understanding the dynamics. But yes, so a proper analysis of this leaves all these parameters free and derives approximate equations for all the parameters from all four orthogonality conditions. And also takes account the dependence of z on beta. So this is a BS. So multiplying both sides by b, you would get n times e to the pi over b, you get this, which is an equation you have to solve for b in terms of s. So you see why it's so important to understand the relationship between sigma and b. So you get the Bs is proportional to minus sigma. Right. So with that equation, then you get b to the 3 e to the pi over b sub s is equal to, if you work that out precisely, it is this times e to the pi over b sub s, but b squared is subordinate to b, Yeah, so this term is then negligible in comparison. You get minus pi b, bs e to the pi over b. Well, we're only working up to a constant anyway. So we have that, and then you get that is proportional to yeah, I seem to have messed up the sign here. Minus 1. Don't know what I've done with the signs. Yeah, so b is supposed to be decreasing, going to 0. And so we should be getting something negative here. And then over here, I get negative plus, oh yes. So it is a plus, because now I have as b goes to, yeah, okay, so now I have as b goes to 0, this does get large, right? So it should be increasing, and so then we get, so then we can integrate. And we get pi over b. So of course, b to the 3 versus e to the pi over b, the exponential dominates. You know, you could put this up here with the log correction. It's just the e to the pi over b. So you take the log of both sides, you get pi over b is comparable to log s, or b of s is comparable to pi over log s. So that is the behavior of b as a function of s. Finally, get that from all this. Okay, so then we'll do a few more computations and get the values of the rest of the parameters. Once you know b as a function of s, you know that the log of lambda to the minus 1, s derivative of that is minus lambda s over lambda, and that is approximately b. Which again, what would come from at the more rigorous level would come from one of the orthogonality conditions. Take the time derivative of that, and this comes out. This is pi over log s. And so you integrate in s, and the log doesn't vary that much, so this is approximately pi s over log s. The leading order. Integrating would just be approximately multiplying by s. Then you look at d dt of lambda squared log lambda minus 1. Okay, what is that? That is exactly equal to lambda t log lambda inverse with 2 terms. So you know, the derivative lands here, lands there. And so we generate 2 terms, but one of them is dominant. Okay, so that's just direct computation. But we have lambda is going to 0 as we blow up. So terms going to infinity down here, making this term subordinate to the 2. So it's really just 2 times this. So this is, so let's just write it, I'm sorry, so let's just put a 2 there and erase all of that and put an approximate and then plug in what we have. So lambda times lambda sub t is also lambda s over lambda. And that's approximately minus b. So we have minus 2b log lambda inverse. And we found b as a function of s, and we found log inverse as a function of s. So you get minus 2, and I plug in the b, that's pi over log s. And I plug in the value of log lambda inverse, that's pi s over log s. And then this is expanded. You just get the log of s, which is then the dominant term, like log of s minus log s. It's the log of s, which is dominant. So it's log s over log s. So we just get, as s goes to infinity, minus 2 pi. So we find that the time evolution of lambda squared times log lambda inverse is asymptotically constant. And it's from there. So if this weren't present, this log was not present, then that would tell you that lambda should just be t to the 1/2, right? But instead, with that log, we arrive at lambda of t approximately 2 pi t star minus t over log t star minus t inverse to the 1/2 as the exact dynamics. And then you have that ds dt was lambda to the minus 2, so that's approximately log t star minus t inverse over 2 pi t star minus t. So that integrated in t gives you that s of t is 1 over 2 pi log of t star minus t inverse times log of t star minus t inverse. So in the slightly supercritical case that we started with today, this log correction was not here. It was not here. Here. It's missing from here, and then missing from here. So if b is written as a function of s, is pi over log s, and now we know that s is given in terms of t by this, then you can finally recover that b of t is log pi over log of t star minus t inverse. So you get that b of t is going to 0 as t approaches t star very slowly, as this denominator very slowly goes to infinity. And s of t goes to infinity as we approach the blow-up time, and lambda goes to 0 at this precise rate. So there's actually 3 different scales in the problem, all separated by an exponential. you have, so the origin, and then you can go out to distance 2 over b, which is significant because in the construction of the profile z, it turns out to be a classical turning point in the WKB analysis. So there's that. Then there is a sigma inverse, which is like b e to the pi over b. So that's an exponential beyond this distance. And that is in some of the papers called the radiative regime in the dynamics, because the tail of the z profile is still relevant to the analysis. It's an algebraically decaying tail that's then cut off at this radius sigma inverse. And then you can go out to lambda inverse, right, which if the solution is z of the form profile x over lambda t with the 1 over, there's the scale factor in front. But you have your fixed profile that is being scaled in by the factor lambda, then this is the distance that corresponds to lambda, and that is, so we see that the lambda is yet another exponential beyond that, so it's like e to the sigma inverse. If you look at the b here, you have to exponentiate to get the 1 over log, and then you have to exponentiate that in order to get the power. Okay, so it's halfway through, so we'll take a little break at this point, and then I'll discuss some more general considerations about blow-up in the critical and supercritical cases.